Okay, it's recording. Hi, this is Bianca Porter and David Pound, and we will be presenting a slippery slope. We are group 5. On my part of the presentation, I will be calculating slope and intercept as rate of change. I will be identifying quantities that are and aren't good candidates to be modeled with linear or quadratic functions. All right, calculating slope and rate of change. Let's see here. All right, calculating slope and rate of change. The slope of the line tells us how something or the rate changes over time. If we find the slope, we can find the rate of change over that period. This graph shows how John's saving account balance has changed over the course of a year. We can see that he has opened his account with 300 way down here, and by the end of the first month, he saved 100. By the end of the month 12, John had $1,500 in his savings account. John may want to analyze his finances a little more and figure out how much he was saving per month. This is called the rate of change per month. By finding the slope of the line, we would be calculating the rate of change. And the next slide will show you more about rate of change using the same problem. This is John's saving account balance of the year. Let's look at John's graph again. John would like to find out how much money he saved per month for the year. In other words, John wants to know the rate of change per month. We are finding out how much John's account changes per month on average. We see that he is starting off at $300. On the graph, the point is 0,300. His ending account balance on month 12 is $1,500. The point is 12, 1,500. Therefore, our two ordered pairs are 0,300 and 12, 1,500. We can now use the slope formula to find the slope of the line. The slope is the rate of change from one month to the next. The slope is equal to 100. This means that the rate of change is $100 per month. Therefore, John saves on average $100 per month for the year. And down here, it shows the problem: the beginning balance, the ending balance, the formula, and the slope. All right. So next, I'll be identifying quantities that are and are not good candidates to be modeled with linear and quadratic functions. So for a linear model, the function would be y equals mx plus b. When its graph is going to form a straight line. So whatever you see a linear equation or model on a graph, it's going to be a straight line. The slope is going to be constant. When x goes up by 1, y goes down by 3. The changes are always constant on a linear function. All right, so for example, here is a linear equation or table. On x, it goes up by 1, 4, 3, or 0, 1, 2, 3, 4. Then on y, it's 10 to 7 is -3, 7 to 4 is -3, 4 to 1 is -3, 1 to -2 is -3, and then -2 to -5 is -3. On the y side of things, the changes are always going to be constant, and the slope is -3 over 1, which is describing this table right here for the linear function. So next we move on to the quadratic function. Sorry about that. The function would be y equals ax by the second power plus bx plus c. When it's on a graph, it's going to form a parabola line, which is the u on the graph. It looks like a u. The change in the change of the y is constant. So when they say the change in the change, which means I kind of wrote out an example right here. So the x is going to be 1, 2, 3, 4, 5, 6. It's going to go all the way down to 6. And what they mean by the change of the change is, okay, first it's going to be 4, 6, 6, 4, 0, 6. So that's the first one. So what we do is we go right here. 4 to 6 is 2. 6 to 6 is 0. 6 to 4 is -2. 4 to 0 is -4, and so on and so on. But what it's not doing, it's not constant. See, it's 2, 0, -2. So what we have to do is we have to go again what would be the change or the difference in the difference or the change in the change. So we have to do it again one more time to see if that number would be constant. So what we do is we use the second pair of numbers. Would be 2 to 0 would be -2, right? 0 to -2 would be -2. See how those numbers are constant right there? -2 to -4 is still -2, and so on, so on. As long as these numbers are constant, that what gives you a quadratic function. Alrighty, I will be passing it off to and these are my references. And now I'll be passing it off to my other group member, Dava Pound, and she will be going more into detail about linear and quadratic functions.
Very good. You did very good with your present. Good job, Bianca. You did really good. Okay, so I'm going to share my screen. Again, forgive that I'm on my phone, but sometimes you gotta do what you gotta do.
Yep.
Mommy. Hush. I love you. Nicole, hush. Oh, dang it. What happened? Okay. So I will be talking about the linear quadratic modeling with solving them algebraically to go off of Bianca, and then also show how you can do it with technology. So with linear modeling, it describes a continuous response of a variable with one or more predictor variables. It helps you understand and predict the behavior of complex systems or analyze experimental, financial, or biological data. So with this example, I used pizza and toppings. So as you can see, 0 toppings on a pizza is an automatic cost of $6. So going with a pizza costing $6, 1 topping means $8, and so on and so on, which means it's increasing by 2. And so our equation that we would use is y equals 6 plus 2x. 1 pizza costs $6, and each topping each costs $2. So whatever y is, or whatever x is, would multiply that by 2, and then you would go from 6 plus the product of that and get the total amount for how much your pizza will be. With quadratic modeling, it's the process of finding the equation of the parabola that best fits in a set of data. As a result, we get an equation of the form y equals ax squared plus bx plus c, where a cannot equal 0. So here, use an example of a baseball being hit at a point of 3 feet above the ground, going at a velocity of 100 feet per second. And the path is given by the function f of x equals negative 0.0032x squared plus x plus 3, where the height of the baseball in feet and x is the horizontal distance from home plate in feet. What is the maximum height reached by the baseball? For the quadratic, really? What did it just say? Okay. For the quadratic function, you have f of x, which implies that a equals negative 0.0032 and b equals 1. With finding the maximum height, we will do x equals negative b divided by 2a. So here 1 is our b, and our a is negative 0.0032, which 1 divided by that is 156.25 feet. And then the height, you would multiply it, take it from, you would plug in the feet for every x to come out with 81.125 feet. Linear modeling. This is with the technology, and I used Excel as the example. You enter all your data in the Excel worksheet, and then select the data by dragging the cursor over the cells. Click the Insert tab, and then click the Scatter Chart icon in the ribbons chart groups. Select the first scatter chart in the drop-down below menu, and it will appear in your worksheet. And then right-click any data point in the chart and select Add Trend Line from the drop-down menu. And then you would examine the trend line, also called the regression line. To do this, you click on the display equation on the chart to check a checkbox, and the formula that appears on the chart is the regression equation in the form of y equals rx plus a. Sorry, my glasses. Where the y is a predictable score or predicted score of any x value, and is the line slope, and a is the y-intercept. Using Excel to do quadratic modeling is a little bit more steps, but you tell Excel that you want to join the big leagues by clicking the Data Analysis Command button on Data tab, and then you select the regression tool from the analysis tools list, and then press OK. Here, the next steps would be identify your y and x values by putting them side by side in an Excel worksheet. And then you would you would input the y range text box, and then identify also for your x range of how far you want it to go. And here's some examples of how to do that. And then selecting the constant, zero. You're looking for your zeros. Sometimes you're not going to have any limits. I'm so sorry. Okay. To calculate your regression analysis, you select the confidence level checkbox, and then on the confidence level, you enter what confidence or which value you want to use. So okay, this is what I was talking about. Going back to where you want to return at to find the probability plots. You add the residual and normal probability information into the regression analysis results, and then you press OK. And it should come out to be something like this. It might be a little bit blurry, but it's going to show you exactly where your zeros are, if there is any zeros, and it also shows you your maximum and minimum heights. And there's some references. Although
I like how you use Excel.
Although mine might have been a little. Do what?
I like how you use Excel for that, to just, to break down linear and quadratic models.
Yeah, I mean, Excel is what we already use, so to already use it as the technology instead of a calculator. I mean, we're in modern days now, so we're in Excel a lot. So might as well just use that as how you're going to be able to find it. And although it might have been hard to see on the screen, there's the steps that you can follow. And I actually tried it myself, and it came out to be exactly how you're supposed to. So this is Group 5 with Bianca Porter and David Powell. And we hope you enjoyed it, even though it might have been a little chaotic on my side because it's on my phone. But I do apologize. So you can never give negative for effort, right?
Well, I'm Bianca Porter.
And I'm Diva Pound.
And this is a Slippery Slope Group 5.
Hope y'all enjoyed it. Have a good night.